James Webb has just revealed something astonishing. A planet with a 99.7% chance of hosting life. The telescope detected unmistakable signs in its atmosphere, including water vapor, methane and dimethyl sulfide, molecules associated with biological activity. This isn't just a distant exoplanet. It's a world that seems chemically alive, with oceans, clouds and atmospheric processes suggesting that life could thrive there. What is happening on this alien world, and could it be the first proof of life beyond Earth? Stay with us, because the implications are more profound than anyone imagined. The story began not with a photograph or a dramatic flash of light, but with a line of numbers sliding across a monitor in a darkened control room. In the silence of space, a few photons that had travelled for 120 light-years arrived at humanity's newest window to the cosmos, the James Webb Space Telescope. They carried whispers of chemistry, faint distortions in infrared light so delicate that only a gold-mirrored eye suspended a million miles from Earth could catch them. Thousands of scientists around the world spend years preparing Webb to read such whispers. Its mirrors, 18 hexagons perfectly aligned, were cooled until they were colder than Pluto's surface, allowing them to see heat from objects too faint for any other telescope. When those photons from the constellation Leo reached the detectors, they were converted into data streams that looked, to the untrained eye, like static, yet within that static a pattern pulsed, small, rhythmic, impossible to ignore. At first it appeared routine. Webb had been targeting a planet known as K2-18b, a super-Earth orbiting a small red dwarf star. Previous missions like Kepler and Hubble had hinted it possessed water vapor, but no one expected anything more dramatic. The goal was simple: refine its atmospheric measurements. What arrived instead was something that didn't fit into any known chemical model of a lifeless world. Each wavelength told a piece of the story. The data revealed dips and rises, spectral fingerprints that corresponded to molecules suspended in the planet's air. Carbon dioxide, methane, water vapor, but then, hidden inside those familiar markers, appeared a faint curve that shouldn't have been there. Analysts at Cambridge and NASA cross-checked their calibrations, assuming noise or a misalignment. Still the signal persisted, subtle yet steady, defying every effort to erase it. Niku Madhusudan, leading the Cambridge exoplanet team, examined the sequence frame by frame. The signature matched a compound he knew too well: dimethyl sulfide, or DMS. On Earth, this molecule is born only from living things, mainly oceanic plankton, releasing gases that shape clouds and climate. No volcano, storm or chemical reaction in a sterile atmosphere can create it. When the algorithms confirmed the match, his disbelief gave way to a quiet electric awe. Verification demanded months of scrutiny. The Webb team reran the observations at different orbital phases, ensuring sunlight filtering through K2-18b's atmosphere produced the same spectral fingerprint each time. Independent instruments aboard Webb, including the near-infrared spectrograph, confirmed it. Noise models were applied, subtracted, recalculated. The probability of error fell to less than 3 in 1,000. In statistical terms, a 3 sigma detection, 99.7% confidence. In emotional terms, the first serious evidence that life might exist beyond our solar system. While numbers confirmed the discovery, imagination struggled to catch up. Light that left K2-18b during Earth's medieval era had finally revealed its secret. Each photon carried a record of conditions across an alien sky: a hydrogen-rich atmosphere, warmth hovering near 49 degrees Celsius, and an intricate balance between heat and pressure capable of sustaining liquid oceans below the clouds. The realization was staggering. Humanity's instruments had reached across centuries of time and trillions of kilometers to glimpse another possible cradle of biology. Back on Earth, the news spread quietly through encrypted channels before public release. Teams at NASA's Goddard Center and the European Space Agency cross-verified the datasets. The faint line corresponding to DMS remained visible after every correction. There was no contamination from Webb's optics, no interference from Earth's atmosphere, no instrumental ghosting. What remained was pure signal, chemical breath exhaled by something alive on a distant world. K2-18b itself is enormous compared to Earth, roughly 8.6 times more massive, wrapped in a hydrogen-helium envelope that softens sunlight and maintains extraordinary stability. Its orbit lies squarely in the habitable zone, where water can exist in liquid form. The planet's star, cooler and smaller than our Sun, provides steady illumination without violent flares. Combined, these traits create a thermal harmony seldom found in the universe. For life, it is paradise written in physics. The scientific implications reached far beyond one planet. If DMS could appear in such an environment, then biology need not depend on Earth-like oxygen atmospheres at all. Hydrogen-based ecosystems could be thriving around countless red dwarfs scattered through the galaxy. Astronomers began re-evaluating data from other super-Earths once dismissed as too gaseous or too massive. The search for Earth 2.0 suddenly felt naive. The cosmos seemed far more inventive. Behind closed doors, the research teams debated how to present the finding without overstatement. No one wanted a repeat of past false alarms. They drafted language carefully. We have detected potential biosignature gases consistent with biological activity. Even this cautious phrasing carried revolutionary weight. For the first time, science had crossed from speculation to measurable evidence. Late at night, when the data stream slowed and the servers hummed softly, some researchers allowed themselves to wonder about the source. Was K2-18b's surface covered by a deep ocean exhaling DMS into the air, like Earth's plankton seas? Were microbial colonies drifting beneath a hydrogen sky, unseen yet powerful enough to alter planetary chemistry? These thoughts remained unspoken in papers, but they haunted every analyst who stared too long at that spectral line. As Webb continued its silent watch from the L2 point, the telescope itself became a symbol, a machine that had reached beyond imagination and found something living in the darkness. Humanity for the first time wasn't merely asking whether life existed elsewhere. We were observing its chemical shadow across the void. What could this faint molecular breath tell us about the world it came from, and what lay hidden beneath those alien clouds? Stay with us as the mystery deepens. The morning the data arrived. The first public trace of the discovery began in quiet corridors, not in headlines. When the encrypted data packet from the James Webb Space Telescope reached the Cambridge exoplanet servers that December morning, it was timestamped 0517 UTC. Outside, the English winter sky still slept behind fog. Inside the lab, soft blue monitors painted scientists' faces as terabytes of infrared information scrolled into storage. No one yet grasped that humanity's place in the universe was about to shift. Webb had completed a series of transit observations on the planet known as K2-18b. Each time that world slipped in front of its parent star, starlight passed through its atmosphere and carried fingerprints of the gases it contained. Those thin traces of filtered light had travelled for 120 years before being captured by the Webb's cold sensors. What arrived on Earth was a compressed map of an alien sky, light that had left K2-18b when Einstein was still a child. Data engineers initiated the standard calibration routines first. They removed background radiation, corrected for telescope jitter, and aligned wavelength references with atomic standards. As the clean spectra appeared, the usual features showed up clearly: deep absorption lines where water vapor and methane absorbed the star's light. These were familiar, expected, almost reassuring. But within hours, the software flagged a faint irregularity in one of the near-infrared bands. The anomaly was subtle, buried under thousands of legitimate signals, yet it repeated across multiple observation runs. In astronomy, repetition means reality. Niku Madhusudan joined the session mid-morning, carrying the calm of routine that scientists cultivate to guard against false hope. For months, his team had been refining a new retrieval algorithm designed to separate overlapping spectral features. When he ran the latest data through it, the curve sharpened and an extra dip emerged, exactly where none should exist. The shape corresponded to dimethyl sulfide, DMS, an organic compound produced on Earth by marine life. Madhusudan paused, checked the noise model again, and said nothing. The room stayed silent except for the soft whir of processors digesting light from another world. Rather than celebrate, the team turned to skepticism, the instinct of every cautious researcher. Could Webb's mirror alignment have introduced an artifact? Could cosmic rays have mimicked a chemical signature? They compared the suspect wavelengths with calibration lamps and with blank sky exposures taken minutes before the planet's transit. The spectral feature persisted only when the planet was in view. It was not hardware, not background, not software. It was the planet itself speaking through its chemistry. Verification required more than excitement. Cambridge sent the raw data to collaborators at NASA Goddard, and the European Space Agency for independent analysis. Separate pipelines, different software, different calibration constants, produced the same result within margins smaller than human hair widths. Scientists who had spent decades looking for ambiguity now confronted clarity so sharp it felt unreal. By early afternoon, the focus shifted from disbelief to quantification. Every astronomical discovery lives or dies by statistics. The teams calculated confidence intervals, applying a method known as sigma testing. When the numbers stabilized at 3 sigma, corresponding to 99.7% confidence, the room filled not with noise but with controlled breathing. That level of certainty matched the benchmarks used to confirm gravitational waves and Higgs bosons. What they held was no coincidence. Outside of these closed analyses, the world went on unaware. Students crossed courtyards slick with rain, commuters scrolled through phones, telescopes elsewhere pointed at other stars. Inside the data center, however, an invisible frontier had been crossed. The spectrum on the monitors represented not theory but observation. A living planet's atmospheric fingerprint detected for the first time in history. Evening brought further checks. Webb's detectors, floating 1 million miles from Earth at the L2 Lagrange point, were inspected for thermal drift or contamination. Engineers reported stable performance. The mirror temperature remained near minus 233 degrees Celsius, ensuring pure infrared sensitivity. The data integrity log showed no anomalies. Every system confirmed what the spectral lines implied. Something on K2-18b was producing DMS in measurable abundance. Across time zones, more specialists joined the analysis. Astrobiologists compared the DMS signal with the Earth-based reference spectra measured from oceanic phytoplankton. The match was uncanny. Planetary modelers examined whether non-biological processes could explain the molecule under hydrogen-rich conditions. Simulations failed to reproduce it without invoking life. The simplest explanation, biology, remained the strongest. As midnight approached in Cambridge, fatigue mixed with a strange stillness. The scientists understood the magnitude of what lay before them, but also the caution it demanded. In research culture, extraordinary claims require extraordinary proof. They drafted preliminary memos. Evidence suggests the presence of dimethyl sulfide in the atmosphere of exoplanet K2-18b, every word weighed carefully, every adjective measured to avoid exaggeration. The data was archived in redundant servers, mirrored in 2 continents, encrypted to protect integrity. Yet within those encrypted files lay humanity's most intimate revelation, that life may not be singular. What Webb had captured was not an image, but a connection across cosmic distance, a chemical echo from an unseen ocean or cloud system that, somewhere beyond the Leo constellation, might still be alive this very moment. When dawn returned over Cambridge, the fog had lifted. The streets were ordinary again, but the world was not. Somewhere light was already leaving another star, carrying new secrets toward Webb's golden mirrors. Each photon on its way could hold another fingerprint, another answer waiting to be found. What deeper mysteries would unfold once the faint signals from K2-18b were fully decoded? Come with us to explore the hidden corners of the story. The hidden world of K2-18b, as new photons from the distant constellation. Leo streamed toward the James Webb Space Telescope. The scientists who had first seen the dimethyl sulfide signal turned their focus from disbelief to exploration. If the data were true, they needed to understand the world that had sent such a clear chemical voice across interstellar space. Numbers on a monitor now had to become geography, atmosphere, and physics, a portrait of a living planet. The first layer of that portrait came from orbital mechanics. K2-18b circles a cool red dwarf star about 120 light-years away, completing one revolution every 33 Earth days. Its distance from the star, though smaller than Mercury's orbit, places it within the so-called habitable zone, because the dwarf's gentle output delivers roughly the same energy per square meter that Earth receives from the Sun. In the quiet mathematics of exoplanet science, that ratio defines the possibility of liquid water, and thus of life. The telescope's next task was to measure mass and radius with precision. Transit timing variations and radial velocity data from previous missions, refined by Webb's infrared observations, revealed a planet about 8.6 times heavier than Earth and 2.6 times larger in diameter. That combination meant that K2-18b sits between rocky super-Earths and icy mini-Neptunes, a class scientists call Hycean worlds, planets likely wrapped in hydrogen-rich atmospheres above deep global oceans. It was the first time a confirmed Hycean candidate showed chemical hints of biology. Atmospheric modelling converted those measurements into temperature and pressure profiles. Webb's instruments detected a steady equilibrium near 49 degrees Celsius, about 120 degrees Fahrenheit, at the upper cloud layers. Below that, the pressure rose smoothly, consistent with a thick hydrogen-helium envelope capable of distributing heat evenly from the daylight hemisphere to the dark. Unlike Earth, with its sharp day-night contrasts, this planet appeared almost thermally uniform. An endless twilight warmed from within and without. Spectra revealed more than warmth. Alongside dimethyl sulfide came clear signatures of methane, carbon dioxide and water vapour, each verified at multiple wavelengths. The absence of ammonia, which theoretical models predicted for lifeless gas giants, suggested active chemical cycling. On Earth, similar patterns emerge only when living systems consume certain molecules faster than they can accumulate. It was the first chemical hint that K2-18b's atmosphere might be self-regulated rather than inert. From those measurements, planetary scientists began constructing vertical cross-sections: altitude versus composition, temperature versus density. In those diagrams, a striking possibility appeared. If the atmosphere transitioned smoothly into liquid at higher pressures, then beneath the haze could lie an ocean hundreds of kilometers deep, water mixed with hydrogen, stable across a vast temperature range. Laboratory experiments on hydrogen-water mixtures at high pressure show that such fluids remain liquid from near freezing to well above 150 degrees Celsius. On K2-18b, that meant a sea unlike anything in our solar system, neither purely aqueous nor purely gaseous, but something in between. Gravity shaped everything. With 3 times Earth's surface gravity, the atmosphere would be compressed but also firmly anchored, preventing the slow escape that stripped Mars long ago. That gravitational hold, combined with the planet's magnetic shielding from its star's mild radiation, would allow its gases and potential oceans to persist for billions, even trillions of years. Stability on that scale gives biology time, an essential ingredient more precious than water or warmth. Attention then turned to the host star itself. Red dwarfs like K2-18 emit most of their light in infrared wavelengths, exactly the range Webb was built to study. Unlike many red dwarfs known for violent flares, K2-18 is unusually calm, its output steady and predictable. Stellar activity monitoring from both Webb and ground-based observatories confirmed a placid energy curve. For any life beneath those crimson skies, that constancy would mean security from radiation storms that could sterilize less protected worlds. Each new analysis reinforced an unsettling truth. This planet might be more stable, more forgiving, and perhaps even more life-friendly than Earth. Its hydrogen atmosphere works as an immense insulator. Its star burns with unwavering gentleness. Its oceans, if confirmed, could endure beyond the lifespan of our own sun. The data painted not a barren sphere, but an ecosystem's foundation written in chemistry. Within research circles, the name K2-18b began to appear beside phrases once reserved for imagination: habitable super-Earth, biosignature candidate, Hycean exemplar. Peer-reviewed preprints detailed every variable, from spectral resolution to model uncertainties, emphasizing caution, yet carrying an unmistakable sense of wonder. For the first time, the search for life had produced not speculation, but a structured, testable environment that matched the conditions for biology in more than one independent measurement. As the findings spread, other observatories prepared follow-up campaigns. The Hubble Space Telescope's archival data were reprocessed with Webb's calibration constants, revealing weaker hints of the same chemical ratios years earlier, signals overlooked because the instruments then lacked the necessary precision. What once seemed noise now appeared as prelude. The scientists who had received that morning's data packet realized they were witnessing the boundary between discovery and comprehension. Every new calculation peeled back another veil. A planet balanced perfectly between gas giant and rocky world, between alien and familiar. K2-18b was no longer an anonymous entry in a catalogue. It had become a mirror reflecting how limited Earth-based definitions of habitability had been. If this much complexity could exist around a small, quiet red star, What might await around the hundreds of billions of others scattered through the galaxy? Let us guide you into what no one expected. Through alien air. Every world begins with light. For the K2-18b, that light comes from a red sun whose glow never reaches the eyes of those who study it. Instead, the light is broken apart into its invisible components, analysed and reassembled into the story of an atmosphere. To move from numbers to understanding, scientists had to imagine themselves not above the planet, but inside it, tracing each molecule through its dance between sky and sea. The James Webb Space Telescope's spectrographs had already proved that K2-18b's skies were not thin. Their readings showed a vast envelope dominated by hydrogen and helium. Yet within that simple mixture hid extraordinary complexity. Hydrogen molecules, the smallest in nature, scatter infrared light differently from heavier gases. By measuring exactly how much starlight dimmed at each wavelength during a planetary transit, Webb could reconstruct how the atmosphere's density changed with height. Those patterns revealed that the air thickens gradually, rather than abruptly, evidence that heat circulates efficiently from the planet's star-facing side to its eternal night. Inside that envelope, subtle chemical variations told a second story. Methane levels appeared higher than expected for a purely abiotic system, while ammonia, predicted by chemical equilibrium models for a lifeless hydrogen world, was conspicuously absent. When modelers at the University of Cambridge and NASA Goddard ran simulations to reproduce the observations, only scenarios including ongoing chemical depletion of ammonia matched the data. On Earth, similar depletions occur when microorganisms consume nitrogen compounds. The implication was profound. Something on K2-18b might be altering its own atmosphere faster than geology alone could manage. Temperature mapping came next. Using Webb's near-infrared spectrograph, researchers measured the thermal emission on both the day and night hemispheres. The readings showed less than a 10-degree difference between them, a stunning level of uniformity given the planet's tight orbit. Such balance means the atmosphere behaves like a planetary engine, moving heat around with astonishing efficiency. It also ensures that water, if present, remains liquid across nearly the entire surface, rather than freezing or boiling away. This consistency supports the Hycean world model that had begun to redefine the boundaries of habitability. Within these atmospheric layers, light and chemistry interact in ways alien to human experience. Red dwarf starlight is rich in infrared radiation, but poor in ultraviolet. On Earth, ultraviolet photons drive reactions that form ozone and protect life from excessive radiation. K2-18b's weak UV flux would produce far less ozone, yet its dense hydrogen mantle likely compensates, scattering energetic particles before they can reach the depths where life, or its precursors, might reside. In laboratory simulations, hydrogen has proven to be an efficient shield, absorbing high-energy cosmic rays and reducing surface radiation by orders of magnitude. The same physics could be at work there. To test these ideas, researchers combined Webb's results with theoretical spectra generated from high-pressure experiments on hydrogen-water mixtures. When matched against observations, the model spectra aligned so closely that even minute deviations became diagnostic tools. At certain altitudes, carbon dioxide features suggested the formation of photochemical hazes, microscopic particles created when sunlight breaks apart methane. Those hazes would tint the planet's clouds with subtle hues and help maintain thermal stability by reflecting part of the incoming starlight. Though no telescope can yet see them directly, their spectral fingerprints leave no doubt that K2-18b's skies are dynamic and layered. The question then shifted from what was present to how it behaved. Airflow models indicated that unlike Earth's jet streams driven by rotation and solar heating, K2-18b's winds might be governed primarily by convection within its thick atmosphere. Slow-rising columns of warm hydrogen could transport heat upward, while cooler parcels sink, creating vast rolling systems that blur the boundary between weather and climate. For any future probe, decades away at best, such currents would pose challenges unimaginable in Earth's thin air. Beneath those winds, chemical gradients likely govern the exchange between atmosphere and ocean. High-pressure experiments show that hydrogen dissolves readily in water under K2-18b-like conditions, forming a continuous medium rather than a distinct air-sea interface. This means gases could circulate from ocean to sky and back again, sustaining equilibrium over geological timescales. For scientists, that circulation is more than a curiosity. It is a mechanism through which biosignatures like dimethyl sulfide could accumulate to detectable levels. By late 2023, multiple research groups had published independent confirmations of Webb's findings, peer-reviewed analyses in the Astrophysical Journal. Letters detailed how the planet's spectra compared with model atmospheres of differing compositions. Each approach converged on the same conclusion: a hydrogen-rich, water-bearing world orbiting quietly in the habitable zone of a small, stable star. None of the models could reproduce the observed chemistry without invoking processes that on Earth are biological in origin. The data continue to be refined as Webb collects new transits, but already K2-18b has become a template for what astronomers now call non-Earth habitability. Its atmosphere proves that life's possible homes are broader than once imagined, not only oxygen-blue worlds but also crimson giants wrapped in hydrogen fog, where chemistry writes its story in wavelengths instead of words. Standing at the edge of that understanding, scientists find themselves asking, what kind of life could endure beneath such skies? And how many other worlds like K2-18b might be waiting in the archives of light still to be read? Stay here as the next twist unfolds. The molecule that shouldn't exist. Each measurement from K2-18b had expanded the frontier of known chemistry, but one spectral signature stood apart from the rest. When the Webb team separated the wavelengths again, the pattern of absorption aligned with a compound that, in all earthly experience, appears only when something living is at work. Its identity, dimethyl sulfide DMS, a molecule so delicate that even on Earth it survives only briefly in air before breaking apart in sunlight. The recognition came not from a single graph, but from a chain of confirmations. Webb's near-infrared imager detected a faint dip around 3.4 microns, while the spectrograph showed complementary absorption near 6 microns, precisely the pair expected for DMS's SAM-S and C-H bonds. When those features remained consistent across multiple transits, instrumental error could no longer explain them. In planetary spectroscopy, 2 independent wavelength matches constitute strong evidence. 3 or more approach certainty. Here, 5 separate channels agreed. To ensure nothing terrestrial had slipped into the data, engineers traced every stage of the signal's journey. They checked the telescope's cryogenic filters, compared dark frame readings, and modelled the background glow from Webb's mirrors. No contamination fit the pattern. The DMS signature appeared only when the planet crossed its star, vanishing whenever the telescope turned elsewhere. That simple on-off rhythm was proof that the molecule belonged to K2-18b alone. On Earth, DMS forms through marine biology. Microscopic plankton synthesize a compound called dimethyl sulfonopropionate to regulate internal pressure. When cells rupture, sunlight and bacteria transform it into dimethyl sulfide, which drifts upwards to seed clouds and influence weather. No known volcanic, photochemical, or abiotic pathway can reproduce its exact spectrum at planetary scale. The realization that the same fingerprint emerged from a world of hydrogen clouds left researchers in a rare silence. The next step was quantitative. How much of this molecule could Webb's detectors actually see? Using radiative transfer models, scientists estimated a mixing ratio on the order of parts per billion, astonishingly high for a biosignature gas detectable across 120 light-years. For that concentration to persist, production on the planet would have to be continuous, implying an active cycle replenishing it as fast as it decayed under radiation. The atmosphere was not static, it was chemically alive. Skeptics demanded alternative explanations. Could photochemistry in a hydrogen atmosphere mimic DMS without biology? Modelling teams introduced every plausible reaction: methane interacting with sulfur dioxide, lightning generating transient sulfur chains, even meteoritic infall. None yielded the required spectral shape or abundance. The residual curves always diverged. The conclusion, reached independently by 3 research groups, was that non-biological synthesis could not account for the signal within known physics. This did not mean scientists proclaimed life without caution. In public briefings they used careful phrasing, potential biosignature, consistent with biological activity. But privately the excitement was unmistakable. a compound exclusive to living systems on Earth, had appeared in data from an exoplanet, and it had done so with a confidence level exceeding 99%. The field of astrobiology, once dominated by the theoretical arguments, suddenly had an empirical case study. Follow-up observations soon extended the picture. DMS did not exist alone. It co-occurred with methane, carbon dioxide and water vapour, a combination that suggested active carbon and sulfur cycles. On Earth, these molecules interact through metabolism and climate feedbacks. Organisms release gases, the atmosphere processes them, and new compounds return to the surface. K2-18b showed the same interdependence. The spectral ratios hinted at equilibrium far from what chemistry alone would maintain. Statisticians calculated the probability that such alignment could arise by chance. When all molecular signals were combined, the chance of random coincidence dropped below 1 in 10,000. In observational astronomy, that level of coherence is exceptional. Even discoveries of exoplanet atmospheres rarely exceed a single sigma. The Webb results reached 3. The numbers, free of sentiment, carried their own quiet authority. Attention turned to implications. If DMS truly marks biological activity under hydrogen skies, then life might not require oxygenated atmospheres at all. Instead, metabolism could revolve around sulfur and carbon, using hydrogen as both solvent and energy carrier. This realization forced a re-examination of thousands of archived spectra from previous missions. Worlds once dismissed as uninhabitable, too large, too gassy, suddenly became potential habitats in disguise. Astrobiologists also noted what the signal lacked. No trace of ammonia appeared, though chemical equilibrium predicts it should dominate in a lifeless hydrogen environment. The only process capable of removing it efficiently is biological consumption. Together, presence of DMS and absence of ammonia formed a pattern too specific to ignore. Chemistry alone could not sculpt that balance. As the analysis matured, a new phrase entered the literature: biosignature ensemble, a set of molecular relationships whose combined probabilities exceed any single indicator. K2-18b became the first verified example. Each compound reinforced the others, converging on one conclusion: a system driven by reactions reminiscent of biology, yet operating under alien conditions. For many researchers, the moment carried philosophical weight. Humanity had built an instrument capable of sensing not only planets, but the faint chemical breath of another ecosystem. It was not a photograph of oceans or forests, but a spectral code speaking across time. Decoding that message would demand years, perhaps decades of continued observation. What deeper transformations inside that hydrogen sea could generate such unmistakable molecules? And could they point toward life forms beyond any earthly comparison? Come with us as the secrets grow even darker. 120 degrees of perfection. When researchers calculated the planet's thermal profile, the result felt almost implausible. K2-18b's atmosphere maintained an average temperature close to 49 degrees Celsius, about 120 degrees Fahrenheit, a reading that, in planetary terms, balanced on the fine edge between scorching and sustainable. For a world 8 times heavier than Earth, and wrapped in hydrogen, equilibrium of that kind seemed improbable. Yet Webb's instruments confirmed it repeatedly, each observation tracing the same steady warmth. The measurement came from the telescope's mid-infrared detectors, which record the faint glow of heat leaving a planet as it passes behind its star. By comparing light before and after the eclipse, scientists could deduce how much energy the atmosphere absorbed and re-radiated. The numbers painted a portrait of a planet neither freezing like Mars nor boiling like Venus. Instead, it hovered in a zone where molecular motion proceeds quickly enough for chemistry to flourish, but not so quickly that structures fall apart. Heat stability at that scale is no accident. Models show that K2-18b's thick hydrogen shell traps and redistributes energy with remarkable efficiency. Convection currents move warmth upward, while infrared-absorbing gases such as methane and carbon dioxide prevent abrupt cooling. The outcome is a world without the violent temperature swings that define most planets. Even the hemisphere locked in perpetual darkness, common for close-orbiting worlds, remains temperate because the gases transfer heat seamlessly across the terminator line. To verify the precision of those values, astronomers compared Webb's findings with theoretical predictions derived from radiative transfer equations. Every test returned consistency within a few degrees. Achieving such accuracy across interstellar distance demanded careful calibration. Mirror temperatures held at -233 degrees Celsius, background emissions filtered, and statistical uncertainties reduced through months of repeated transit observations. The result stands among the most precise thermal readings ever obtained for an exoplanet. A stable 120 degrees Fahrenheit environment transforms how scientists think about habitability. Laboratory studies of extremophiles on Earth show that complex biochemical reactions can operate efficiently up to about 120 degrees Celsius, with many thriving near 50 degrees Celsius. On K2-18b, that temperature could accelerate metabolic processes if any exist. Warm water enhances molecular mobility, allowing organic compounds to collide, bond, and evolve more rapidly. It also prevents the global freezing that limits biological diversity on colder worlds. The discovery forced a reassessment of planetary climate design. Earth's temperature balance arises from a delicate exchange between sunlight, clouds, and greenhouse gases. K2-18b achieves similar moderation through a completely different recipe. Hydrogen instead of nitrogen, a red dwarf star instead of a yellow sun, and an atmosphere several times thicker than ours. Despite these contrasts, both worlds settle near the same energetic sweet spot, a coincidence that hints at universal physical principles governing life-friendly climates. Scientists found the symmetry striking. The planet receives roughly the same amount of stellar energy per square meter that Earth gains from the Sun. Its red star emits mostly infrared light, which the hydrogen envelope absorbs and re-emits evenly. That natural filtering softens extremes, producing what researchers describe as a radiative greenhouse equilibrium. It is a condition neither too reflective nor too opaque, maintaining steady warmth for eons. This stability extends beyond temperature. Because red dwarfs evolve slowly, K2-18's luminosity will remain almost unchanged for trillions of years, far longer than the Sun's lifespan. The heat balance observed today could persist through cosmic epochs, giving any potential ecosystem immense time to adapt and diversify. From a planetary science perspective, time equals opportunity. On K2-18b, the clock runs indefinitely. Thermodynamic modelling further suggests that such an atmosphere resists runaway effects. On Venus, excess carbon dioxide amplifies heating until the surface becomes molten. In contrast, hydrogen's high heat capacity allows K2-18b to absorb and distribute energy without tipping into instability. Even modest increases in stellar output would be buffered by the gas's ability to carry heat upward and radiate it back into space. It is, in effect, a built-in climate regulator. The measurement of 120 degrees Fahrenheit also provided insight into planetary composition. Combined with density data, it implied the existence of a thick, volatile layer over a denser interior, perhaps a rocky or icy core capped by an extensive ocean. At pressures predicted for those depths, water mixed with hydrogen could remain liquid across an enormous range, bridging the boundary between sea and sky. Thermal continuity from surface to atmosphere would further stabilize the planet's energy flow, sustaining its chemical cycles over geological timescales. When the research papers appeared, headlines emphasized the temperature because it was tangible, warmth one could imagine feeling on skin. Yet behind that single figure lay a revolution in planetary climatology. K2-18b demonstrated that habitable conditions need not mirror Earth's blueprint. Physics alone, operating under different materials and colors of light, can sculpt a climate gentle enough for life. The numbers also redefined scientific ambition. Detecting a planet's temperature to within a few degrees across 120 light-years proves that humanity's instruments can now reach the threshold of environmental characterization. The next logical step is not simply to find more planets, but to compare their climates, searching for the statistical patterns that reveal where life prefers to arise. K2-18b's warmth, consistent yet mysterious, stands as both measurement and metaphor. In a universe dominated by extremes, it represents balance, proof that nature can engineer comfort from chaos. The telescope's data do more than describe physics. They whisper of equilibrium written into the fabric of distant skies. What hidden systems maintain that perfect balance beneath the clouds, and could they conceal the rhythms of an unseen ocean world? Walk with us into the truth that was never meant to surface. A blanket of hydrogen and light. From the first glimpse through telescopes, K2-18b presents itself as an enigma wrapped in a veil of gas. Its hydrogen-rich atmosphere is unlike anything found in our solar system. Where Earth wears a thin coat of nitrogen and oxygen, K2-18b swathes itself in a dense, shimmering hydrogen shell, capable of redistributing heat across the globe. Day and night, as measured by the rotation of the planet beneath its sun, are blurred. Temperatures stabilize in a quiet rhythm, creating an almost eerie consistency that defies our earthly intuition. Researchers describe this layer as a living skin. Hydrogen, the lightest and most abundant element in the universe, dances through the atmosphere in currents that move heat, disperse energy, and shield the surface from the star's occasional flares. Unlike Earth's atmosphere, where storms surge and winds rage unpredictably, K2-18b's hydrogen mantle flows almost like water, carrying warmth in a ceaseless loop from the side facing its red sun to the dark side cloaked in shadow. The planet's distance from its star might suggest a chill world, yet the hydrogen acts as a thermal buffer. Heat absorbed on the sunlit side never accumulates into deadly extremes, nor does the darkness plunge into lethal cold. Instead, temperatures hover in a range that, on Earth, would be called mild. This phenomenon has scientists envisioning oceans that, while hidden, could remain liquid for eons, an environment where chemistry has the luxury of time to play its intricate games. Yet the atmosphere is more than just a climate moderator. It is a shield against radiation. Red dwarfs like K2-18 can erupt in powerful flares that, on other planets, might strip away atmospheres or obliterate life. Here, the hydrogen cocoon absorbs and diffuses much of that energy, softening its impact. Beneath it, any surface or ocean exists with a protection that Earth has never known. This safety, born of elemental abundance, allows for the possibility of life developing in ways we cannot fully imagine. The thickness of the hydrogen layer creates otherworldly skies. Light from the red dwarf star filters through the gas, producing soft glows and faint colour shifts unseen on Earth. Researchers speculate that any observer above the clouds might witness sunsets that stretch for hours, with hues dancing between crimson, amber and violet, refracted through the infinite folds of hydrogen. Even eternal darkness might hold shimmer and glow as light bends, scatters, and saturates every layer of gas above the surface. Understanding how this blanket works has required precise observation and complex modelling. Using infrared spectroscopy, scientists have traced how heat moves through the atmosphere. They detect signatures of water vapour, methane and other molecules interlaced with hydrogen, hinting at interactions that stabilise the climate and maintain the planet's equilibrium. These patterns suggest that the atmosphere is far from inert. It is a dynamic, self-regulating system that continuously adapts to shifts in radiation and temperature. Pressure within the hydrogen shell is staggering. Any hypothetical visitor descending through the clouds would encounter crushing weight, far exceeding what humans experience on Earth. Yet for microbial or exotic life forms adapted to these conditions, this pressure could be nurturing rather than destructive. Dense hydrogen could facilitate chemical reactions that, on Earth, require catalysts or laboratory equipment, turning K2-18b into a vast natural laboratory for organic processes. Every observation hints at balance, an atmosphere tuned perfectly to its star and planetary mass. Unlike Earth, which experiences chaotic weather patterns, K2-18b's envelope creates a steady, almost meditative environment. Yet within this seeming calm, subtle motions churn. Currents rise, fall, and spiral, carrying energy like silent veins across the planet. Scientists speculate these flows might even generate weak magnetic effects or drive chemical cycles critical to sustaining any biosphere below. K2-18b challenges our very definitions of a habitable world. It is not Earth-like, yet its atmosphere produces stability and protection beyond anything in our system. A blanket of hydrogen, unassuming at first glance, transforms the planet into a place where extremes are muted, chemistry thrives, and perhaps life could linger undisturbed for millennia. Could such a world wrapped in its eternal hydrogen cloak hide oceans alive with possibilities just beneath the clouds? Let us tell you. The ocean beneath the clouds. Beneath K2-18b's dense hydrogen veil lies a world hidden from sight, where light barely penetrates and pressure mounts to levels that would crush a human without protective technology. Yet, in this extreme environment, scientists detect a promise: water, not frozen, but liquid, stretching in an ocean that could span hundreds of miles in depth. Unlike Earth's shallow seas and turbulent currents, this ocean exists in a realm of extreme pressure where hydrogen mixes with water to form a stable, fluid layer resilient to temperature swings. The consistency of the atmosphere above provides the rarest of gifts in planetary science: stability. Spectroscopic studies of K2-18b's atmosphere reveal subtle traces of water vapor, hinting at exchanges between the clouds and this hidden ocean below. The detected molecules suggest that the ocean is not a stagnant body, but one capable of interacting with the atmosphere, cycling chemicals, and perhaps even generating energy gradients that could drive complex chemistry. Unlike Earth, where oceans freeze and evaporate seasonally, the hydrogen buffer ensures this alien sea remains liquid across eons, giving molecules, and potentially life, the time to assemble intricate patterns. Dimethyl sulfide DMS has been observed in the planet's air, a molecule linked on Earth to microbial processes in oceans. While not conclusive evidence of life, the presence of DMS raises a tantalizing possibility that chemistry within this alien ocean is active, even biological. On Earth, DMS plays a role in cloud formation and atmospheric balance. On K2-18b, its presence could indicate a planetary system where life or prebiotic processes contribute to atmospheric stability, making the planet's climate self-regulating in ways unseen anywhere else. Pressure and composition define the character of this ocean. Models suggest that as one descends, hydrogen begins to dissolve into the water, creating a fluid medium capable of unique chemical interactions. Minerals dissolved from the rocky interior might interact with hydrogen-rich water, forming compounds rare on the Earth. Energy sources for any potential biology could be derived from chemical gradients, not sunlight, providing a foundation for life in complete darkness. It is an ocean where energy flows silently through reactions invisible to the naked eye, yet powerful enough to sustain long-term chemical activity. Tidal forces from the planet's star could gently stir this vast liquid expanse. Even though K2-18 is a red dwarf and the planet likely experiences tidal locking, gravitational interactions might create subtle currents in the ocean, distributing heat and nutrients evenly. Unlike Earth's turbulent tides, these currents would be steady, flowing with a rhythm dictated by gravity, pressure, and chemical density, forming a quiet yet persistent circulation that could aid in chemical equilibrium. The depth and extent of the ocean remain speculative but essential for understanding the planet's potential for habitability. Some researchers posit that it could reach far into the planet's interior, bordering high-pressure ices, or interacting with silicate layers below. Others suggest a shallower, more accessible liquid layer, perhaps capped by a thick cloud deck of hydrogen and water vapor. Both scenarios present environments vastly different from any Earth ocean, yet each offers conditions where chemical complexity, and potentially life, could flourish over millions or billions of years. Even the dynamics of heat within the ocean are unlike anything familiar. The thermal blanket above prevents dramatic cooling, while pressure suppresses boiling, creating a calm yet dynamic system where heat moves slowly, allowing chemical reactions to persist. Molecules might circulate through convection currents, slowly transforming simple compounds into complex chains. Unlike Earth's ocean where sunlight drives photosynthesis, K2-18b's ocean could rely entirely on chemical energy from the planet itself, powered by interactions between hydrogen, water, and other trace molecules. The combination of pressure, liquid water, and a chemically active environment makes this ocean a candidate for exotic life, beyond Earth-like biology. Life here would not depend on oxygen. It could metabolize hydrogen or methane, extracting energy from chemical imbalances rather than sunlight. Microbial communities could form dense networks, exchanging compounds, regulating the atmosphere above, and leaving subtle signatures detectable only with precise spectroscopy. Every molecule of DMS, every trace of methane, tells a story of possible processes at work deep beneath the clouds. What fascinates scientists most is the planet's enduring consistency. For billions of years, this ocean might have existed in near-perpetual equilibrium, offering time for processes to unfold in ways impossible on Earth. Stability over geological timescales means chemistry could experiment on the planet without interruption, assembling molecules that might never form elsewhere. In a universe defined by chaos and unpredictability, K218b offers a rare haven of persistent invisible activity beneath its hydrogen canopy. Beneath its pressurized hidden ocean, might K218b harbour life the universe has never seen? Could it support systems that, though alien to us, follow the fundamental patterns of biology? Come with us to know the planet that rains diamonds. Above the hidden ocean of K2-18b, the atmosphere transforms into a stage of spectacle where chemistry performs in a display both dazzling and mysterious. Observations suggest that the planet's upper layers host a remarkable phenomenon, the formation of diamonds. Methane, carried upwards by atmospheric currents, encounters intense pressure and temperature, forcing carbon to crystallize into diamonds. These diamonds begin their endless descent through thick hydrogen clouds, refracting faint light from the red dwarf star, creating a shimmer that could blanket the sky in perpetual brilliance. Unlike the fleeting sparkle of meteors or terrestrial diamonds, these crystals fall continuously, a cycle dictated by the planet's chemistry and gravity. The diamonds are not mere ornaments. They are a natural consequence of atmospheric physics, a signal of the extreme conditions that define K2-18b. In this environment, pressure reaches levels that on Earth could not be replicated in any laboratory without sophisticated equipment. It is a testament to the strange, alien processes that dominate planets beyond our solar system. The implications extend beyond beauty. Diamond formation in the upper atmosphere provides evidence of a dynamic chemical system where elements move, react, and restructure themselves under relentless force. Carbon freed from methane condenses, forming solid particles that eventually fall. This process is intertwined with atmospheric circulation, thermal gradients, and the distribution of other trace gases. Each crystal that drops may interact with hydrogen and water molecules along its path, contributing subtly to the chemical equilibrium that sustains the planet's stability. Researchers study these phenomena using spectroscopy, analysing the way starlight filters through K2-18b's upper layers. Patterns in light absorption reveal the composition of the atmosphere, confirming the presence of carbon, methane, and other compounds capable of forming solid crystalline structures. Unlike Earth, where geology and tectonics form diamonds over millions of years, here the process is immediate, occurring in clouds hundreds of kilometers above the unseen ocean, a continuous loop driven by pressure, chemistry, and temperature. This diamond rain also offers clues about the internal workings of the planet. If carbon is so abundant in the atmosphere, it likely originates from deep reservoirs within the planet itself. K2-18b may possess a carbon-rich interior feeding methane into the atmosphere through geological or volcanic processes. The interaction between surface, interior, and atmosphere reflects a tightly coupled planetary system, where each layer contributes to the extraordinary phenomena visible from afar. The visual spectacle of diamond precipitation is complemented by its potential effects on the planet's energy balance. Falling diamonds may scatter starlight, subtly influencing temperatures and chemical reactions in the upper layers. The refracted light could contribute to slow heating patterns, maintaining conditions that allow water to remain liquid far below. These interactions suggest a world where physics and chemistry combine in continuous feedback, sustaining stability while creating beauty unimaginable on Earth. The existence of this diamond cycle challenges human perception of value and rarity. On K2-18b, such crystals may be as common as raindrops, abundant yet integral to the planet's environmental equilibrium. They are not objects to be mined or treasured, but byproducts of planetary processes, essential components of the system's chemical balance. Each diamond represents a fingerprint of the planet's chemistry, an indicator of the pressures, temperatures, and elemental makeup that define K2-18b's alien ecosystem. Furthermore, the diamond rain may indirectly signal the presence of other complex chemical activity. Methane, a precursor to diamonds, is also a potential indicator of biological or prebiotic processes in certain environments. While the formation of diamonds here is abiotic, the coexistence of methane, water, hydrogen, and trace organic compounds suggests a world rich in reactive chemistry, where molecules can assemble, break apart, and recombine in a system that is both stable and alive with transformation. K2-18b's diamond showers also provoke philosophical reflection on the diversity of planetary systems. On Earth, rain sustains life, carving valleys, nourishing ecosystems, and shaping landscapes. On K2-18b, rain becomes something simultaneously artistic and functional. Diamonds refract starlight, carry carbon through the atmosphere, and maintain chemical balance. The familiar idea of precipitation takes on a new meaning, emphasizing that planetary processes can be both beautiful and essential, even when they seem otherworldly. Scientists continue to model the mechanics of diamond formation, examining how pressures in the upper atmosphere, combined with hydrogen-rich layers and temperature gradients, create conditions impossible to replicate artificially. These studies illuminate not just K2-18b, but broader questions about exoplanets, how chemistry, pressure, and temperature interact to produce phenomena unlike anything in the solar system. K2-18b becomes a laboratory of extremes, offering insights into planetary physics that challenge assumptions rooted in earthbound experience. As these diamonds cascade endlessly, they hint at the interconnectedness of the planet's systems, from atmospheric chemistry to hidden oceans, from internal geology to the gentle but persistent rays of its distant star. Each crystal tells a story of pressure and chemistry, of processes that have likely continued for millions of years without pause, shaping an environment as alien as it is mesmerizing. Hidden beneath its clouds and oceans, could this planet, where rain falls like art and chemistry moves with perfect precision, be harboring even deeper secrets? Let us guide you into what no one expected. The star that never ages. Beyond the swirling clouds and diamond rains of K2-18b, the planet's fate and stability are anchored to a remarkable celestial companion, its star K2-18. Unlike our Sun, a volatile yellow dwarf with a finite lifespan of roughly 10 billion years, K2-18 is a red dwarf, a stellar entity defined by patience, endurance, and quiet resilience. Its cooler surface temperature emits a soft red glow, unassuming from a distance, yet offering one of the most stable stellar environments known in astronomy. For the planets orbiting it, this longevity is not just a curiosity, it is the very framework that shapes possibility. Red dwarfs like K2-18 burn their hydrogen slowly, stretching lifespans across trillions of years. In practical terms, this means K2-18b exists under the watch of a star that will remain unchanged for epochs far beyond human comprehension. There is no looming solar aging, no supernova countdown, no rapid evolution of brightness or radiation. Every day on K2-18b, whether under the faint light reflected through hydrogen clouds or in the shadowed regions of its oceans, occurs within a stellar system of unparalleled continuity. This endurance provides a stable energy input, a prerequisite for any long-term chemical or biological processes to unfold below its protective atmosphere. K2-18's gentle red light penetrates the planet's hydrogen envelope just enough to sustain subtle energy gradients. These gradients, while invisible to the human eye, influence atmospheric circulation and heat distribution. Unlike more luminous or erratic stars, K2-18 delivers a steady flow of photons, reducing fluctuations that could destabilize the planet's climate. In essence, the star does not dictate violent weather or extreme seasonal shifts. Instead, it nurtures a quiet, almost meditative consistency, a rare gift for any world dependent on stable energy flows to maintain oceans, chemical cycles, and potentially life. Stability extends beyond temperature. Red dwarfs like K2-18 are known for infrequent but sometimes intense stellar flares, yet the combination of distance and the planet's hydrogen-rich atmosphere creates a natural buffer, absorbing radiation and mitigating bursts of energy. The result is a planetary environment that balances between exposure and protection, where the star's energy is harnessed rather than threatening, allowing processes below the clouds to continue uninterrupted. It is an equilibrium rarely achieved on worlds orbiting volatile stars. K2-18's smaller mass compared to the Sun also shapes the orbital dynamics of K2-18b. The planet likely experiences tidal locking, with one hemisphere always facing the star. In other systems, this could lead to a scorched day side and a frozen night side. On K2-18b, however, the hydrogen atmosphere redistributes heat so effectively that such extremes are softened. The star's consistency allows for an environment where chemical reactions in the ocean and atmosphere are not subjected to sudden shifts, permitting long-term stability and a rare opportunity for complex molecular systems to endure. The star's light spectrum, dominated by infrared, interacts uniquely with the hydrogen-rich atmosphere. Infrared penetrates more deeply than visible light, subtly warming layers otherwise shielded by thick clouds. This selective energy transfer helps maintain liquid water beneath the clouds and ensures that chemical gradients persist in the ocean below. Energy is delivered not in bursts or spikes, but as a continuous flow, creating conditions for reactions to accumulate, molecules to assemble, and potentially life to experiment with long-term survival strategies. K218's longevity also reframes the concept of evolutionary time. On Earth, life has emerged, diversified, and reshaped the biosphere in mere billions of years. On K2-18b, with a star that may burn for trillions of years, life, or chemistry approaching life, could unfold at a pace unthinkable on our planet. Complex molecules could form, degrade, and reform countless times, exploring paths that might never stabilize on faster-moving worlds. This temporal luxury creates opportunities for molecular diversity that stretch far beyond the narrow windows available on planets around shorter-lived stars. For scientists, K218 is more than a distant sun. It is a laboratory of time. Its steady output provides a rare baseline against which atmospheric, oceanic, and chemical processes on K2-18b can be studied. By observing how the planet reacts to this unchanging star, researchers can explore how habitability evolves under extreme stability, offering insight into the types of worlds where life could emerge and persist in the universe. Even the faint variations in K218's output, subtle shifts in infrared intensity, or occasional microflares, interact with the planet's atmosphere to produce gentle, persistent circulation patterns. These patterns ensure that energy is distributed evenly, sustaining the ocean beneath and maintaining a delicate chemical balance. In this sense, the star is not just a provider of light and heat, it is a partner in the planet's ongoing equilibrium, a cosmic choreographer silently guiding the rhythms of the world below. Might the steadfast constancy of K2-18, radiating quiet energy over trillions of years, be what allows K2-18b's hidden ocean and complex chemistry to flourish undisturbed. Stay here as the next twist unfolds. The machine that saw the invisible. 1,000,000 miles from Earth, beyond the pull of our planet's shadow and the turbulence of its atmosphere, the James Webb Space Telescope drifts in silence at the second Lagrange point. Here, in near-perfect isolation, it peers into the cosmos with eyes tuned to infrared, capturing the faintest whispers of heat and light that would be invisible to any other instrument. In doing so, it has become humanity's most precise detective of distant worlds, revealing secrets hidden within the atmospheres of exoplanets like K2-18b. The telescope's gold-coated mirrors are more than shiny metal, they are instruments of revelation. Optimized for infrared, they collect photons that have traveled tens of light-years, bending and reflecting them with unmatched precision. Webb can detect energy signatures fainter than a single candle on the moon, distinguishing between the glow of a planet and the overwhelming brilliance of its star. Every photon captured carries a story: the composition of clouds, the presence of water vapor, and the faint traces of molecules that hint at chemical, or even biological, processes far beyond our solar system. Webb's chronographs act like surgeons' tools in space, blocking the blinding light of stars to reveal the delicate glow of planets orbiting them. In the case of K2-18b, these instruments have isolated the planet's infrared signature with remarkable clarity, exposing patterns of energy movement within its hydrogen-rich atmosphere. These patterns allow scientists to determine temperature gradients, the circulation of heat, and the movement of gases, transforming the telescope into a window not just on distance, but on dynamic planetary processes occurring in real time. The data collected by Webb goes far beyond simple detection. Spectroscopy allows the telescope to deconstruct the light passing through K2-18b's atmosphere, identifying specific molecules based on their absorption and emission patterns. Water vapor, methane, and dimethyl sulfide emerge from the analysis, each revealing a layer of the planet's chemistry. Unlike Earthbound observations, which are limited by atmosphere and light pollution, Webb measures these signatures with the precision required to distinguish real planetary phenomena from noise, contamination, or interference. Artificial intelligence on board the telescope plays a crucial role. Algorithms sift through millions of data points, differentiating subtle atmospheric fingerprints from background radiation. Every adjustment, every calibration is designed to ensure that the chemical patterns observed are authentic, not artifacts of measurement. For K2-18b, this process has allowed scientists to confidently claim the presence of molecules associated on Earth with biological activity, raising the stakes in the search for extraterrestrial life. Infrared observation provides another advantage. It penetrates the clouds and hazes that obscure visible light. For K2-18b, the dense hydrogen atmosphere and thick clouds conceal the planet's surface, but infrared penetrates deep enough to reveal interactions between the atmosphere and the ocean below. By tracking variations in heat distribution and molecular absorption, scientists can infer the presence of dynamic processes, such as chemical cycling or potential metabolic activity, without ever directly observing the surface. Webb's precision is a testament to human engineering, yet its role extends beyond mechanics. It has become a bridge between imagination and proof, capable of turning speculation into measurable data. Before Webb, signs of water, complex molecules, or biosignature gases on distant worlds remained uncertain. Now, each observation carries weight, rooted in measurement, cross-validation, and statistical certainty. Its findings are not guesses. They are tangible records of chemical and physical realities unfolding light years away. The telescope's location at L2 is crucial. At this gravitationally stable point, Webb experiences minimal thermal interference from the Sun, Earth, or Moon, allowing it to maintain extremely low temperatures necessary for infrared detection. Cooling to near absolute zero, the telescope can capture faint heat signatures without background noise, ensuring that even the slightest energy emission from K2-18b is detected with clarity. The resulting images and spectra provide insights into atmospheric composition, temperature profiles, and potential signs of life, all while preserving the delicate structures that make such detection possible. Through its instruments, Webb becomes an interstellar biologist, peering at the rhythms of a planet light years away. Every spectrum analyzed and every photon measured illuminates the previously invisible, translating faint signals into a language humans can understand. For K2-18b, the telescope has unveiled the intimate connection between atmosphere, ocean, and chemical potential, creating a foundation for questions that only time and further observation can answer. Are the faint infrared traces Webb observed hinting at activity, mysterious processes that stretch our very concept of life? Stay close as the layers continue to peel back. The mathematics of certainty. When the data from Webb arrived on Earth, it was more than numbers and spectra. It was a dialogue between probability and truth. Astronomers do not work in certainties, they work in confidence intervals, statistical significance, and cross-checked models. For K2-18b, every observation of water vapor, methane, or dimethyl sulfide was subjected to rigorous analysis, filtered through layers of computational validation, and tested against countless models of noise and interference. The mathematics behind these measurements became the silent arbiter of discovery. Detection of potential biosignatures relied on what scientists call a sigma threshold. A 3 sigma detection, the standard applied to these molecules, corresponds to a 99.7% probability that the signal is real, not a product of random variation or instrumentation error. Reaching this level of certainty is painstaking. Webb's data is not taken at a single moment. It is collected across multiple transits, with variations analyzed for consistency. Every spectral line is scrutinized to ensure that it's truly from the planet's atmosphere, not an artifact of stellar light, cosmic radiation, or detector noise. Redundant verification is central to the process. Independent research teams cross-reference results using different algorithms and statistical models, each iteration narrowing uncertainty. Simulations of planetary atmospheres, including temperature gradients, cloud opacity, and chemical interactions, are compared against the observational data. When multiple models converge on the same signature, confidence grows. In the case of K2-18b, Each signature detected reinforced the previous, building a web of evidence that surpassed any threshold of mere plausibility. Mathematics is not abstract here. It is the language through which the universe communicates. Every molecule identified in K2-18b's atmosphere, every trace of water, methane, and dimethyl sulfide emerges not as speculation, but as a quantifiable entity with defined probability. Statistical techniques allow scientists to separate the faint whisper of the planet's atmosphere from the overwhelming glare of its star. Techniques like Bayesian analysis refine confidence levels, helping researchers distinguish between real planetary chemistry and coincidental spectral overlaps. The concept of false positives is central to the validation. In exoplanetary science, signals can be misleading. Stellar variability, instrumental drift, or interstellar medium interference can mimic the presence of molecules. To claim discovery, scientists must calculate the likelihood of such errors. For K2-18b, each molecule's detection was compared against potential false positives. Only when the probability of misidentification dropped below rigorous thresholds could the presence of chemical signatures be considered statistically robust. Beyond confirming existence, mathematics allows scientists to estimate quantities and interactions. Concentrations of molecules, their vertical distribution in the atmosphere, and their interactions with clouds and heat currents are derived from complex equations solving radiative transfer, pressure gradients, and chemical kinetics. These models translate the raw photons captured by Webb into tangible insights. The presence of a hydrogen-water ocean, dynamic chemical cycles, and energy gradients capable of sustaining long-term molecular activity. Uncertainty is never fully eliminated, but it is quantified. Error margins accompany every reported measurement, giving researchers a clear framework for interpretation. Scientists can express, for example, that the abundance of dimethyl sulfide falls within a specific range, with defined confidence intervals. These boundaries provide both caution and direction, enabling the scientific community to build theories based on rigorous probability rather than conjecture. The precision achieved in these calculations is unprecedented. Earlier telescopes could detect water or methane in broad strokes, but Webb's infrared capability, combined with its stable location at L2 and sophisticated calibration, allows measurements with orders of magnitude greater sensitivity. Minute fluctuations in spectral absorption, previously lost in noise, now reveal patterns of atmospheric circulation, chemical interactions, and thermal dynamics. Mathematics transforms these faint signals into a clear map of the planet's physical and chemical landscape. The implications extend beyond K2-18b. Establishing high-certainty detection sets a benchmark for exoplanetary research, demonstrating that distant worlds can be studied with confidence approaching that of laboratory experiments. Probability becomes the bridge between the impossible distance separating us from these planets and the undeniable reality of their existence, structure, and chemical processes. Every sigma calculated, every confidence interval verified, ensures that humanity is not interpreting faint signals through wishful thinking. The results tell a story grounded in the rigor of logic and statistics, revealing K2-18b as a planet where chemistry is active, oceans may exist, and potential for life cannot be dismissed. It is a reminder that discovery is built not on hope alone, but on careful, quantifiable proof. Is it through the lens of precise mathematics that the universe whispers its secrets, turning faint signals into undeniable evidence of life? Let us know you. Chemistry that breathes. Beneath the shifting hydrogen clouds of K2-18b, the atmosphere is not a static layer of gas, but a living dynamic system. Heat circulates through currents like blood through veins, carrying molecules from one layer to another, mixing, reacting, and stabilizing the environment in a rhythm that resembles a pulse. Dimethyl sulfide, a molecule linked to microbial activity on Earth, drifts within these currents, hinting at unseen processes below. Its presence suggests that the planet's chemistry is not merely passive, it is active, almost sentient in the way it balances itself. Researchers studying the spectra note how the hydrogen-rich atmosphere amplifies and distributes these chemical interactions. Methane, water vapor, and trace organics rise and fall in delicate patterns, cycling between the deep hidden ocean and the upper layers. These cycles maintain equilibrium, preventing extremes in temperature or composition. In essence, K218b's chemistry behaves like a living organism, continuously adjusting to internal and external forces, sustaining a stable habitat far more effectively than any earthly ecosystem. The interaction between ocean and atmosphere is subtle but profound. Pressure forces hydrogen to dissolve into water at depth, enabling reactions that might be impossible at surface levels on other worlds. Minerals from the rocky core could interact with this hydrogen-rich solution, creating complex chemical pathways that distribute energy and molecules in a quiet, continuous flow. Unlike Earth's reactive ecosystems, which depend on sunlight or photosynthesis, these reactions could proceed in perpetual darkness, insulated by layers of gas and water. Every molecule detected in the atmosphere is a messenger. Methane may originate from geological sources, but the consistent patterns observed suggest more than random distribution. Dimethyl sulfide, rare in planetary atmospheres, indicates processes capable of transforming energy and matter, hinting at interactions that could sustain molecular networks over immense timescales. The chemistry here is not merely the product of physics, it is a system capable of maintaining balance, adjusting to fluctuations in temperature and pressure, and preserving conditions that could nurture life in forms entirely alien to Earth. Scientists describe the system as breathing, a metaphor that captures the flow of gases, the cycling of heat, and the movement of energy between layers. Currents in the hydrogen atmosphere distribute heat from the day side to the night side, while dissolved hydrogen in the ocean allows chemical energy to move vertically, from the seafloor to the cloud tops. The system adapts, responds, and sustains itself, creating a world where chemical complexity can unfold uninterrupted for millions of years. Observations through Webb's infrared instruments reveal variations in molecular concentrations that hint at active processes. These are not static signatures frozen in time. They fluctuate, rise and fall in a pattern consistent with self-regulation. The planet's chemistry is a network with feedback loops that stabilize atmospheric pressure, redistribute heat, and maintain chemical gradients. It is a quiet symphony, invisible from afar but precise, ordered and persistent. This understanding reframes habitability. On K2-18b, the presence of chemical activity alone, without the need for oxygen, sunlight, or Earth-like conditions, suggests that life or lifelike processes may exist in forms we cannot yet imagine. The planet's chemistry does more than react, it orchestrates. It is a system that preserves energy, sustains molecular networks, and potentially lays the groundwork for life that thrives without Earth's conventions. Might this delicate interplay of molecules, invisible yet detectable, be the first sign of life beyond Earth? A silent pulse resonating through hydrogen clouds? Come with us to explore the hidden corners of the story. Life beyond oxygen. In the crushing depths of K2-18b's hidden ocean, sunlight never penetrates, yet energy flows in ways unimaginable on Earth. Here, chemistry replaces light as the engine of potential life. Hydrogen and methane serve as fuels, powering reactions that could sustain organisms adapted to extremes, thriving where oxygen is absent and conventional metabolism fails. The planet's environment allows molecules to interact uninterrupted, creating the conditions for entirely alien biochemistry to emerge. Researchers consider the possibility of life forms that do not breathe oxygen, instead drawing energy from hydrogen gradients, methane cycles, or chemical disequilibria in the ocean. These processes may resemble Earth's chemosynthesis, observed near hydrothermal vents, but on a planetary scale magnified by the thick hydrogen envelope and the constant pressure that maintains liquid water. Energy circulates through the ocean and atmosphere in a steady rhythm, providing the raw materials for molecular systems to grow, replicate, or sustain themselves. Spectroscopic evidence from Webb shows molecules like dimethyl sulfide and methane, whose presence and ratios hint at active processing. While these signals do not prove life, they suggest ongoing chemical reactions that resemble metabolism. The interactions are not chaotic, they are organized, persistent, and possibly self-regulating. On K2-18b, energy is harnessed in ways that might allow microenvironments to form, sustaining molecular networks capable of long-term stability. Life here, if it exists, would likely be unlike anything familiar. Microscopic organisms that absorb hydrogen, convert methane, or utilize dissolved minerals for energy. Some may form colonies within layers of the ocean, structured to maximize chemical exchange. Others could drift within currents, using chemical gradients to navigate the hidden world. These systems might glow faintly under infrared radiation, invisible to human eyes but detectable through spectral analysis, revealing life not as we know it but as a fundamental expression of chemistry thriving under alien conditions. The planet's stability amplifies the potential for evolution. With K2-18's steady output and the insulating hydrogen atmosphere, chemical systems have eons to experiment. Reactions can unfold slowly. Molecules can accumulate and complex chains might emerge over geological time. Unlike Earth, where sunlight drives rapid biological cycles, K2-18b offers a patient laboratory where molecular systems can explore every feasible pathway, potentially forming structures that adapt, persist, and transform gradually. Hydrogen, the most abundant element in the atmosphere, serves as both medium and energy source. It dissolves into the ocean, carrying heat and facilitating chemical interactions. The pressure at depth prevents boiling, ensuring that reactions can occur in liquid water that would be otherwise impossible on the surface. Methane, cycled between ocean and clouds, could act as a chemical currency, providing energy where photons do not reach. Together, these factors create a self-contained ecosystem of molecules, a planetary-scale chemistry that mimics the dynamics of life without relying on oxygen or sunlight. This perspective forces a reconsideration of habitability. Life does not require conditions that mirror Earth. It can exist in extremes, thriving in darkness, under pressure, and within fluids alien to our senses. K2-18b demonstrates that biology may emerge wherever energy flows, molecules interact persistently, and environments remain stable long enough for complexity to develop. The universe, in this view, multiplies possibilities rather than replicating Earth. Are faint atmospheric signals the only proof of life concealed within unseen chemical systems beneath dense clouds? Stay with us to know what really happened. The red dawn of a new definition. The discovery of K2-18b has transformed the way humanity conceives habitability. No longer is life constrained by the familiar parameters of Earth-like atmospheres, oxygen, or sunlight. The planet's hydrogen-rich clouds, hidden oceans, and active chemical cycles redefine the possibilities of existence. Observations reveal that stability, pressure, and long-term chemical activity may matter far more than conditions we have traditionally regarded as essential. The universe, it seems, is not a mirror of Earth. It is a canvas of infinite variation. Spectroscopic analysis has shown a composition unlike anything in our solar system. Water vapor persists under high pressure, methane cycles through dense clouds, and dimethyl sulfide points to chemical processes capable of sustaining complex interactions. Each molecule, each pattern, is a testament to planetary dynamics that operate independently of our familiar biochemistry. It is a world where energy flows through hydrogen, where chemical disequilibria may act as the foundation of life, and where conditions remain stable over eons, offering unprecedented opportunities for molecular complexity. K2-18b's example forces a philosophical shift as well. For centuries, humanity has projected Earth's conditions onto the cosmos, assuming that life must adhere to a narrow set of parameters. This planet demonstrates that such assumptions are incomplete. Habitability is not a single definition, it is a spectrum, encompassing worlds that operate under physics and chemistry profoundly different from our own. Stability, persistence,